All right, so we're going to take a look here at example number 2 to kind of see how we can use some of the stuff we talked about on the last page. So we want to try to evaluate this triple integral. It's a triple integral of the function z over the solid of E. So E is the solid tetrahedron bounded by the following 4 planes. So it's bounded by the plane x equals 0, y equals 0, and z equals 0. Really quickly, I want you just to think about what exactly do those 3 planes actually look like. Start with just the first one, x equals 0. Think about your x, y, z coordinate system. If x is always a 0, well, if x is always a 0, it seems like that would kind of be the plane that would be moving along the y-axis, right? I'm not going to leave this on the page, so you can feel free to not draw this. But it would kind of be the plane that comes up here, right? Like it's the plane that chops right through the y-axis and goes all the way up in the z direction, right? It's that wall. So that's my like x equals 0. My y equals 0 is going to be something very, very similar. My z equals 0 also something very, very similar. Okay. If I was to kind of put all of those together, I could maybe get a quick sketch of what those planes look like and the plane x plus y plus z equals 1. In fact, I'm going to go ahead and attempt to draw a quick picture down here to get a sense of what this does look like. So here's my x, my y, and my z axes. You can start to tell that over here again, I'm going to shade some spots and then erase. This wall, that's my x equals 0. This next wall is where y is always 0. And this floor, well, that's where z is always 0. And so I can kind of see these as framing in some sort of a room. What we want to do, though, is understand where this last plane comes into play. And this last plane, I can start to see by identifying its intercepts. If I'm interested in my x-coordinate, or where this crosses the x-axis, that means that y and z automatically have to be 0. So you'll notice that I cross out at 1. Similarly, I'll cross out at 1 in the y-axis, and I cross at 1 in the z-axis as well. So if I was to go ahead and actually attempt to draw the portion of this plane that at least exists in this particular quadrant, I'm going to get something like this. And you can start to see some sort of like triangular pyramid shape, right? I can see this kind of triangle down at the bottom. I can see this back wall, this side wall, and then I have this triangle that's like leaning up against all of that and kind of acting like a ceiling. So what I start to imagine doing is that I'm going to be like this little person standing right here on the floor, and I'm inside of that room. And so now I want to start to kind of imagine where the walls. This is what's going to help me try to understand the region and how I can begin to communicate it. So here's where I'm going to start. First, I'll say, well, we sketch a picture of E. We already did that. But now I can go ahead and I might be able to define some things about E. Clearly, it seems that E is a bunch of points, x comma y comma z's, with some restrictions. Here's a couple restrictions. First off, no matter where I walk in there, imagine again, maybe it's a bad example to use a person, but maybe, imagine I have the power of flight, and I can also fly to any height in the room. I could start to ask some questions. First, I'll ask, what's the biggest x-coordinate, or the smallest x-coordinate that I can ever go towards? Take a look at the picture. Think about it. What would be the smallest x-coordinate? If you need to, pause the video so you can think through it. Well, it seems like here, the smallest x-coordinate would be 0. X could definitely be greater than or equal to 0. Okay, notice I could say the exact same thing about y and the exact same thing about z. I have to be in that first octant. But there's a restriction. I can't go as big as I want, right? Like I can't go past that kind of horizontal line that I have sitting down here. That's not going to work well. But I could say this. I know that x plus y plus z has to be less than or equal to 1. Like I can only go out, I can only float out until I hit that kind of triangular shape, and then I know that I've reached a boundary in the room. So this kind of describes the region. And while that's an accurate description, it may not necessarily always be the easiest description, because I want to write a description that gives me a clear indication of a bound, ideally, on, let's say, a floor and a ceiling. So I'm going to go ahead and I'm going to attempt to think about some bounds on the value of z. I would like z to be wedged between two functions. I want to identify what's the floor and what's the ceiling. Now the floor, we've already kind of established. Z has to be greater than or equal to 0. That's not a problem. But imagine you're that little person. If you reach your hand up, or if you start to fly upwards, what is it that you're going to hit? What's the ceiling? What is it that you're going to bump into? You might recognize it's that triangular slanted plane. Now, what I'd like to do is come up with a bound on that, which is actually super easy to do, because from this inequality, I can see that z has to be less than or equal to 1 minus x minus y. And that provides me with a really nice way to say this is how high up you can go. Notice that the max height you can reach totally depends on x and y, because like if I was moving more towards this corner, down there near my red dot, I can't reach up very high. If I move towards the blue corner, I can reach up very high. So depending on what x's and y's are, totally changes the height of the room. So once I have these bounds, I am pretty much good to go on 1/3 of my integral. I can say that my triple integral over e of z dv is equal to, well, now I'm going to have a double integral left because I've already tackled one of the dimensions. The first dimension is my dimension on z, my floor to ceiling. So this is my dz. I have z bounds. And I have to figure out what to do with the remaining bounds. But this is the best part. Once I have this, I can imagine doing what we call a projection. I want to understand, where is my little person kind of walking around? What does this thing look like when I take this projection of my solid into the xy plane? We'll see what I mean by that here in just a second. So I'll say, we then project E into the xy plane and find D. Again, I'm trying to find the floor that I'm walking on. Okay, so when we talk about this concept of a projection, I'm kind of interested in down here, this blue triangle, right? This is kind of like the floor that I can walk on. And I'd like to go ahead and sketch a picture of that blue floor. Now, again, it exists completely in the XY plane. I just want to know where are all the spots that I can walk. So it seems like down here, there's still a connection between what's going to be happening. I can see that I connect with 1 on the x-axis to 1 on the y-axis. And my blue triangle is shaping up right here. So this is my D. And what I'd like to do is to figure out how to describe D. I've essentially reduced my triple integral down to a double integral. So if I can imagine this thing as something with a top, bottom, or left, right, I'm golden. And it should be pretty easy to find the equation of the line that acts as this slant. Take a moment, see if you can find what the equation of that line is, just to make sure you're feeling comfortable with how you could get it. Pause the video if necessary. Okay, the equation that I came up with was negative x plus 1. Once I have this, notice I can now define D. D is equal to a bunch of x comma y points where, let's see, I'm going to treat this as a type 1 region. So I'm going to say my y is bounded by, on the low side, a 0, but on the high side, a negative x plus a 1. And my x is bounded from 0 to 1. Now I've discovered how to kind of fill in this dA and this set of bounds. So now I can say, therefore, my triple integral over E is equal to, and I'm going to set this up now in the same way I did before. Oops, sorry, I'm going to get rid of these brackets here just for the sake of simplicity. And I can see that innermost integral is still intact. I now am thinking about that D region, and since my y bounds have functions in them, they're going to come first. My x bounds will come last, which means I'm going to have, what would the order of those differentials be? Well, yeah, you should be able to see that they should be dy first and dx last. So this is it. This is the setup for my triple integral. And hopefully it doesn't seem too overwhelming. It might seem a little overwhelming, and that's partially expected, but hopefully you can see the connections that a lot of this is building off of old ideas. We're not trying to do anything different. We're just trying to imagine now I'm trapped in a room and there's walls, floors, and ceilings. Okay. I'm going to leave it to you to actually go ahead and try to evaluate this integral. And I'm going to leave you with what the final answer is right here. If, again, pause the video, I would highly recommend doing that. And that way you can test to see if you're getting to the right answer on your own. Okay, so the answer that I'm coming up with ultimately is 1 over 24. Now, if you didn't happen to get that answer and something maybe went wrong, you can take a look at the solutions that I have up online, okay, because I have those posted up there. Again, one final thing that I'll note before we kind of end this portion of the lesson is that I didn't necessarily have to start at the beginning by bounding with a floor and a ceiling. I could have imagined that this little guy had his back maybe, or if it was staring down the x-axis, and maybe there was like this wall behind him, and then this triangular slanted plane would have actually been like a wall in front of him. And if that's the case, I could have imagined started by maybe bounding x, like how small could x be? How big could x be? And I could do a very, very similar sort of a process. Overall, then, there are actually a multitude of different ways that you could set up this integral. In fact, in total, there are 6 different ways that you could set up this particular integral. And all of those ultimately produce the exact same answer at the end of the day. All of them would produce 1 over 24. And if you're interested in what some of those other ways are, you could try to figure some of them out for yourself, or again, in the notes in Blackboard, I have listed out some options there as well. Okay. In the next video, we'll take a look at example number 3.